Hi everyone. So today we're going to continue on 11.3. You might notice that this video is a little different. At the very least, we are on a different page in my OneNote because this is the second time I'm making this video. The first video somehow get corrupted and it didn't upload to YouTube, so I have to redo the video. So hopefully you might notice some continuity errors, but that's how it is. So to talk about undetermined coefficient method, the first thing I want you to pay attention to is the following. Let's say we're given a differential equation. We can actually look at a specific example. Let's say we have this one. Y double prime plus 2y prime plus y equal to e to the 3x plus e to negative x plus 1. So this is the equation that we have done together. We know the solution to this equation is the general solution to this equation is basically this. Is y equal to c1 e to the negative x plus c2 e to the x plus 1 over 16 e to the 3x plus 1 half x squared e to the negative x plus 1. So what I want to talk to you about first, before we actually get into the method that I want to show you, which is titled at the top, Undetermined Coefficient Method, is to understand how the solution is constructed. So in this expression right here, notice that this is my y sub h. That is my homogeneous solution. And then this is technically our y sub p, our particular solution. And if you look at a homogeneous solution, notice that in my homogeneous solution, there are two non-specific coefficients for two terms. So pay attention to the following is that this y sub h has two terms. And why is that? Is because L is second order. Okay, and in this case, our L is the differential operator d squared plus 2d plus 1, which we mentioned before already. And notice that our linear operator dictates what our homogeneous solution is, and it also dictates how many terms we must have. In this case, we have two non-specific coefficients. So if you look at the general solution, the non-specific coefficient usually indicate where the homogeneous solution would be. Okay, and that is dictated by the linear operator L. Now, what happened to our particular solution? So if you look at our particular solution has three terms in it. Why is there three terms in it? In this case, because we can identify f sub 1 to be equal to e to the 3x. F sub 2 is e to the negative x, and f sub 3 is equal to 1. And these three functions combined together form our f. And because of the fact that we have three specific functions put together to form the function f in our non-homogeneous differential equation, we will have three extra terms, one for each of the function f1, f2, and f3. So therefore, because there are three functions f1, f2, f3, in this case, we're going to have three terms. And these three terms are y1, y2, and y3, correspond to f1, f2, and f3. In this case, y1 is 1 over 16 e to 3x, which is basically the solution to this. If I take this d squared plus 2d plus 1 of y1, I would get f1, meaning L of 1 over 16 e to 3x would give you e to 3x. Similarly, y2 is equal to 1 half x squared e to negative x. And because if I take L of y2, I should get f2, meaning in this case, if I take L of 1 half x squared e to negative x, I should get e to negative x. And then y3 is 1 because L of y3 would equal to f3, which in this case, if I do L of 1, I should get 1. And that's how it determined the particular solution. Now, the interesting thing about the particular solution is the following. The particular solution each has a term, and also each term will have a coefficient in front. The only difference is the coefficient in front are specific. So these have specific coefficients. Unlike in the homogeneous solution, where what you have are simply just a arbitrary constant C1, C2, C3, and on. Now, how does that help me? I mean, you already know this. You already know how to identify homogeneous versus particular solution. It's based on basically the coefficient being non-specific, C1, C2, C3, or a specific coefficient, whatever number that might be. So now the question is, how do we use that to our advantage? So this is what undetermined coefficient method basically do. Undetermined coefficient method basically states the following. Let's say you're given a differential equation in the form of L of y equal to f. Okay, or actually maybe I do this. L of y of x is equal to f of x. So we identify the independent variable as x. If this is true, if the function f of x is a solution to a homogeneous equation itself, let's say this equation is m of f of x is equal to 0. Then what we can do is we can transform our non-homogeneous equation into a homogeneous equation. How? Like this. If I take m of L of y of x, since L of y of x is equal to f of x, that means this is equal to m of f of x. And since we know m of f of x gives you 0, therefore this would just give me 0. So therefore now allow me to transform our L of y of x, which is non-homogeneous because that's equal to f of x, into a new equation, m of L of y of x equal to 0. Now, but of course, the problem is that doing so doesn't give us the same answer. But it does give you the following. This method, the reason why, because the following. If I now look at the equation m of f of x equal to 0, or m of L of y of x equal to 0, that equation, because it's homogeneous, it will give us a homogeneous solution, which is easier to find than a non-homogeneous differential equation. And number two is that we should be able to identify the specific term that should be the particular solution, and all I need to do, because I already have the term, all I need to do is simply find the coefficient that go with the term, and therefore allow me to complete the solution. Remember, the only difference between a homogeneous solution versus the particular solution is that particular solution has a specific coefficient. So we can determine that coefficient, then we'll be able to put together the particular solution. So this method basically allows us to do the following. This method reduces solving a non-homogeneous differential equation into simply try to calculate or compute the specific coefficient for the particular solution. And this method is called undetermined coefficient method. Because we're basically looking for those specific coefficients. Now, one of the most important part about doing this method correctly is to identify this linear operator m that would transform our differential equation from non-homogeneous to homogeneous. And we will talk about how to identify this linear function correctly. So the most critical part of this method is to identify the correct linear operator m. So we'll talk about how to do that in a minute, but I do want to kind of show you an example first so that we can kind of see how that works. Okay, so let's try an example. So let's say we want to solve this equation, a pretty straightforward one. Let's say solve y double prime minus y equal to e to the x. Okay, so first I'm going to do is go ahead and rewrite it into differential operator form. So it's d squared minus 1 of y equal to e to x. So remember, this d squared minus 1 is our L. This right here is our f, and in this case there's only one function, so I don't need a subscript for that. To start the process of finding our solution to this, the first thing we want to do is to identify the homogeneous solution first. Okay, so how do we do that? Well, that would be d squared minus 1 of y equal to 0. And I would strongly recommend that you pause the video right now and just go ahead and do that by yourself and see if you figure out the answer. It should not take you more than 32 seconds to complete. Okay, so once you have done that, then you can turn back on. I'm going to continue. So this just become r squared minus 1 equal to 0, which are characteristic equation. That become r1 equal to 1 and r2 equal to negative 1. Those are the two roots. So therefore my equation should be this. As I say, require you no more than 32 seconds to complete. So that is my homogeneous solution. So if I put this homogeneous solution into L, I should get 0. So now here comes the undetermined coefficient method. Okay, so the way to do that is to first identify m. So I'm going to have to next find m. So what does m have to do? Well, what m have to do is that it must be a linear operator. When I put in e to x, which is f, I should get 0. Okay. So this basically kind of require you to remember doing something that we have done before, and that would be like kind of like working backward. So in this case, I'm looking for a differential equation whose solution is e to the x. And so once again, what I want you to do is take a minute to pause the video and try to figure it out and see if you can come up with the answers. And once you figure it out, you can unpause and continue. So I'm going to continue. So if I think about it, e to x is a solution. And e to x has a characteristic root of 1 because e to the 1x. And therefore imply that r minus 1 equal to 0 will be our characteristic equation. And that would come from d minus 1 as an operator. So therefore this tells me that d minus 1 of e to the x should equal to 0. So we can see this is the case. That's e to x prime minus e to x. That is e to x minus e to x, which is 0. So in this case, our differential operator m is basically d minus 1. So we got our differential operator. So now we're ready to start our process. Number 3 is to basically identify y sub p. So how do I do that? This is how we start with our equation d squared minus 1 of y equal to e to the x. What I'm going to do is I'm going to basically apply d minus 1, which is our m, to the entire equation. So then on this side become d minus 1 of d squared minus 1 of y equal to d minus 1 of e to the x. And as already established in second step, that come out to be 0. And d squared minus 1 can be factored, so I'm going to go and factor d squared minus 1. When I do that, that becomes this. And if I look at this correctly, this should have 3 characteristic roots. We have a repeated root of 1, and then a single root of -1. And so the solution in this case should look something like this. Y should equal to c1 e to x plus c2 e to -x plus c3 x e to the x. Notice that this equation should have 3 terms, and it makes sense because the homogeneous solution have 2 terms, and because the differential equation equal to one single function f, that means we must have an extra term to it, and that extra term is right here. The problem, this extra term cannot have a C3, because if it has a C3, it would indicate that all 3 terms are basically generated from the homogeneous solution, and therefore indicate that we should have a cubic differential equation. We don't. In this case, C3 right here is what we refer to as the undetermined coefficient. Because this coefficient should be a particular solution which have a specific value in place of C3, and we just don't know what it is yet. Okay, so therefore identify that this part right here must be what we're looking for, y sub p. So now we have identified y sub p. What we have to do is now find it. How? Well, by finding the undetermined coefficient, which in this case C3. So how do we do that? This is how. Now we're going to try to find the undetermined coefficient. So to do that, that's pretty simple. What we're going to do is we're going to start with our y sub p, which is in this case C3x e to the x. And what we're going to do is simply plug that into our differential equation. Because remember, we call this particular solution should satisfy the equation and give us the function f. Okay, we call L of y sub p should equal to f. So therefore, what I'm going to do is try to plug into L, which is in this case d squared minus 1. So to do that, I do need the second derivative. So I'm going to go and find that first before I plug it in. So I'm going to go and find y sub p prime. And y sub p prime should be, I guess, just product rule. So C3 1d2 plus C3 2d1, so it's e to x. And then if I do y sub p double prime, I should have c3x e to the x plus c3 e to the x plus another c3 e to x. The first 2 terms come from the first term in y sub p prime using product rule, and then the last term come from the second term from y sub p prime. Notice these 2 terms combine, so I can say this is equal to c3x e to the x plus 2 c3 e to x. I would not recommend changing 2C3 into something different. It cannot just be C3 because it's meant to be twice as big as C3. If you change it into something else, then it then show the corresponding, the correlation between the coefficient with x e to x. So I would say leave it with a 2 in front. So now we're ready to combine them. So now what I'm going to do is I'm going to do d squared minus 1 of y sub p, and that should give us e to the x, because it should satisfy the equation. So that means that we have y sub p double prime minus y sub p should equal to e to x. So let's find out. So c3x e to the x plus 2c3 e to x, that's y sub p double prime, minus y sub p, which is c3x e to the x, should equal to e to the x. Notice what happened in this case. These two things subtracted out, and therefore give us this equation. And since e to the x can never equal to 0, I'm safe to cancel them out, and therefore leave me with 2c3 equal to 1, imply that c3 must equal to 1/2. So now I have my undetermined coefficients. Now I'm ready to put together my solution. My solution should be y equal to the homogeneous solution, c1 e to the x plus c2 e to negative x, plus the undetermined coefficient 1/2 with our term x e to the x. There you go. So notice the method is not difficult because it technically reduces solving for this non-homogeneous differential equation into just solving for a constant c sub k, okay, or multiple c sub k, okay. So it basically is just algebra. Okay, it does require you to do some derivative because you do need to plug something into a differential equation. But beyond that, it really doesn't require too many calculus, mainly algebra, solving for something. Now, as I mentioned to you, the most important part about doing this process is to identify the correct linear operator m. So how about I give you a table so that we can use it. So table for identifying the correct linear operator m based on the function f. So here's the table. I'll probably go put two of them side by side. Okay, so one column is f, the other one is m. So if you have f of x, then you would be able to identify what is the proper linear operator that would get rid of or turn it into different homogeneous equation. So start with the most basic one, which is a constant k. Constant k requires the differential operator d, because if you take the derivative of a constant, you get 0. If you have a function x, then this would become just d squared. If you take a derivative of x twice, the first time become 1, the second time become 0. And what happens if you have x to the nth power? Then the linear operator that would annihilate it is be d to the n plus 1. Now, what happened to if you have exponential e to the rx? That would give us the differential operator d minus r. Notice that is what we did right here. We have e to the 1x, therefore the linear operator is d minus 1. Now, what if you have x to the n e to rx? Actually, maybe I start with x. What if you have x e to rx? So that indicates that you have to have a repeated root. So therefore, that becomes d minus r squared. And of course, we can expand this to what happens if you have x to n e to rx. And that would be n minus r to the n, d minus r to the n plus 1. So this table basically deals with all the constant or power function, which is x to the power, exponential function, e to rx, and exponential time and power function, which is like x to n e to rx. What other kind of function do you run into? Well, trigonometric. So trigonometric will be harder to deal with, but it is basically the same process. And because sine and cosine go in pair, they require the same exact operator. So if you have cosine bx or sine bx, collectively, they would have this differential operator, which is d squared plus b squared. Now, what if you have x to the n cosine bx or x to the n sine bx? So if you have that, that will indicate that you have a repeated root of cosine bx and sine bx. And the reason why you repeat a root because the factor get repeated. So then what we have will be d squared plus b squared to the n plus 1. That would allow you to annihilate or get rid of, turn it into a homogeneous differential equation. What if you have e to the ax cosine bx or e to the ax sine bx? So these two indicate that you have a complex root instead of imaginary root like you have just cosine and sine. So to form the complex root, what you do is this. It will be d minus a squared plus b squared. Or this can be written as d squared minus 2ad plus a squared plus b squared. And now the most complicated one will be this one. What if you have x to the n e to the ax cosine bx? Or x to the n e to the ax sine bx? So remember, the x to the n basically just indicate you have a repeated root. So in this case, you basically have d minus a squared plus b squared to n plus 1. So this table basically gives you a way to identify what is your proper m. For most of the function that we're going to be doing, this should help you figure it out. I don't anticipate asking you for anything beyond what's on this table, so I would say you should definitely study these two tables and make sure you memorize them so that you can use the method correctly. So the last thing I want to show you is to start our example. Okay, so how about we do this one? Okay, so let's take a look. So this basically meaning d squared plus 1 of y equal to 2 sine x. So notice it's sine x. So if I go up here and look, sine x would be sine of 1x. So b is 1. Therefore, the differential operator should be d squared plus b squared, or d squared plus 1 squared. So therefore indicate that d squared plus 1 of d squared plus 1 of y would equal to 0. So notice that that gives us d squared plus 1 squared of y equal to 0. So we do have a repeated factor. So let's do the first thing first. Let's identify our y sub h. Okay? So what should be our y sub h? So in this case, y sub h should be the following. Y sub h should equal to c1 cosine x plus c2 sine x. Because d squared plus 1 has a conjugate pair of imaginary roots of 1i. Okay? Now the next thing we're going to do is identify our operator, which we already have, which is d squared plus 1, which we know that m in this case is d squared plus 1. So number 3, we have to identify y sub p. So in this equation, because d squared plus 1 square of y equal to 0, I can say that y sub p, or y, should equal to c1 cosine x plus c2 sine x plus c3 x cosine x plus c4 x sine x. So therefore, in this case, this is my homogeneous solution. This is my particular solution. And notice that in this case, we have two undetermined coefficients to figure out, C3 and C4. And it makes sense because our linear operator m is second degree. So now it's just a matter of trying to figure out what the undetermined coefficient is. So let's go for it. So what I'm going to do is I'm going to now find, in this case, C sub 3 and C sub 4. So what I'm going to do is I'm going to identify that y sub p is C3x cosine x plus C4x sine x. If you take the derivative correctly, C sub p prime should equal to negative C3 x sine x plus C3 cosine x plus C4x cosine x plus C4 sine x. And if you take the second derivative correctly, so these you should definitely pause the video and do it on your own to make sure that you get it right. You should have negative C3x cosine x minus 2C3 sine x minus C4x sine x plus 2C4 cosine x. And now I'm ready to plug it in. So remember the equation y double prime plus y equal to 2 sine x should be satisfied if I plug in y sub p. So therefore, when I plug in y sub p, that becomes y sub p double prime plus y sub p should equal to 2 sine x. So let's see what happens. So that would be negative C3x cosine x minus 2C3 sine x minus C4x sine x plus 2C4 cosine x plus y sub p, which is C3x cosine x plus C4x sine x, and that should equal to 2 sine x. Now notice what happened. The C3x cosine x actually cancel with C3x cosine x right there. The negative C4x sine x actually cancel with the C4x sine x over here, and therefore leave us with this equation. So how do I solve this equation? Well, the way to do that is very simple. First, realize that would mean 2 on the right hand side where I say 2 sine x, that technically is the same as 2 sine x plus 0 cosine x, and therefore indicate that the coefficient negative 2c3 should match with the coefficient 2 because they're both coefficient for sine x on the left side and the right side, and the 2 cosine 2c4 cosine x should match with the other side, which is 0 cosine x. So therefore indicate that negative 2c3 must equal to 2, indicate that c3 must equal to negative 1, and 2c4 must equal to 0, indicate that c4 equal to 0. So therefore combine this together, tell me that y sub p should equal to negative x cosine x plus 0 x sine x, which I'm not going to write. And so finally, we can conclude our solution in this case is y equal to c1 cosine x plus c2 sine x minus x cosine x. There you go. Unfortunately, that's all the time I got. The video is already past 30 minutes. All right, so I'll talk to you again soon in the next video. All right, talk to you later. Bye-bye.